Sorry about that. So, George Balla from Uganda, and currently PhD student with Gisela Fourier at RWTH Aachen University in Germany, and since October last year. And yeah, maybe for those who have been at AIMS, I went also to AIMS Ghana, and I'm very happy to speak in the seminar, and thanks to everyone for joining. So in today's talk, I'll be talking about the symplectic PBW degenerate flag varieties, in particular, mainly about PBW tableaux and defining equations. So maybe before I go ahead, flag varieties are one of the most common objects of study in algebraic geometry. They are algebraic varieties, and mainly to say something in general is usually hard because they are very complicated, just like if one takes any projective variety. So it is hard to say something or to give information about any projective variety. So usually what researchers do, they specialize to some case. So in this case, we shall look at the symplectic flag varieties, but a degeneration of those. And we shall look at some combinatory objects, which we shall know. Actually, they are sisters to younger tableaux with a different feeling. Yeah, and then some defining equations. So in the outline of the talk, in the first part, we will establish the objects of study, which are the complete symplectic origin and the degenerate flag varieties. We shall give the description and look at the defining ideals and homogeneous coordinate rings. In the second part, we shall introduce some combinatorial flavor. We shall describe the symplectic PBW-semistandard tableaux, mainly establish the correspondence with a certain nice monomial basis, which will be useful in our talk. At the end, we shall move towards the proof of the main result. Namely, in the first part, the first step towards that will be to give a basis for the homogeneous coordinate rings of these two varieties, and end by outlining the proof for the statement which gives the defining ideal in the degenerate case. Now, so like said earlier, let's establish these two objects, namely, so let's first look at the complete symplectic flag variety. The original one, most people call it the classical one. Yeah, so one can choose a name. Let's denote it by SPF TN, whereby SP is coming from the symplectic group, because we shall use some kind of geometry from representational theory. This is why we choose this notation. And okay, but first of all, let's understand it from the side of linear algebra. And this is if we take a vector space of dimension 2n, we can choose a basis for this, thereby identifying it with C to 2n. Here we are fixing the field to be C. We can choose any algebraically closed field, preferably of characteristic 0. And so if a sequence of subspaces U1 to Un, one contained into the next one, is called a full flag if the dimension of each subspace appearing at position K is of dimension K, is K, yeah. And in addition, we want each subspace to be isotropic with respect to a bilinear form, which is also non-degenerate, skew symmetric. The name for such a bilinear form is symplectic form. So yeah, we are choosing the one whose matrix is given by ms in minus in, where in is the n by n matrix with ones on the diagonal and zeros elsewhere. Now, the requirement that every subspace is isotropic also means that we want every subspace to be an element of the symplectic Grassmannian, which we are denoting by SPGR-K2N. And this is like the usual Grassmannian. So we have, for a Grassmannian or k-dimensional subspaces, the symplectic Grassmannian will be a subset of this. We want every subspace to be isotropic in addition. Now, like before, like for type A, we can have the Pulika embedding of such a set in order to give it some geometric structure to do geometry with it. Otherwise, like a set, it's difficult to deal with. So we can have an embedding into a projective space. But at this point, let's first adopt some notation, namely for an index in the numbers from 1 to n, let the number 2n plus 1 minus I be I bar. And for a subsequence lying in the numbers 1 to 1 bar, a subsequence j of length j, which is increasing. So this indexing set is usually 1 to 2n, but we are just adopting a new notation. So from n plus 1, we call it n bar and so on until 1 bar. And the need for this notation will be apparent later on. So as usual, we have a subspace of dimension k, and we can associate a matrix. Then we can take the rows of this matrix, and so the basis elements are spanning the rows of this matrix, and we can have the wedge product, and we take the multiples of all this, the class of all this. This will be living in some projective space of some big vector space, which is a K exterior power over our vector space, which we fixed, C2n. And we can associate to such an element, we can associate a Pulika coordinate. So one can ask now, what will be the embedding for the symplectic flag variety? Just like in type A, also here we shall have an embedding into the product of symplectic Grassmannians. Just like we have seen, every subspace is living in a Grassmannian, in a symplectic Grassmannian. So we take the product of all these subspaces, and we can embed this in the product of all projective spaces for all k. This is a very big projective space. We can take the corresponding polynomial ring, which is also very big. It's generated by all these variables xj for all sequences j in this indexing set, for all k from 1 to n. So a good question to ask, if you want to do some computations on this variety, what is finding ideal with respect to this embedding? And if we denote it by I, the first guess would be from type A, because we know in type A, there are already relations called the Pulika relations, which generate the defining ideal. What they are, we can just label them by R, L, J, and the number T. So L and J are sequences, one shorter than the other, and their length lying between 1 and n for the complete symplectic flag variety. The number T is lying between 1 and the length of the shorter sequence. So how do we obtain the elements in the summand or the summands? So what we do, after choosing a T, we choose a subsequence from each of the sequences, a subsequence of length T from the shorter sequence. and then we exchange with the corresponding subsequence in the longer sequence, while keeping every index in its position. And whenever we swap indices, we change the sign of the coordinate, because these coordinates are determinants which aren't symmetric in the indices. So the question is, are these relations enough to generate I? And the guess is that no, because at this point we have seen these relations which come from type A, but they are not telling us when is a subspace isotropic, but we want every subspace to be isotropic. So we should need, or we need more relations which are giving us the isotropic condition. So let's try to find out how this come up. So let's consider the symplectic Grassmannian of two-dimensional subspaces in C6. Let's take U2 of a subspace of dimension 2 in this symplectic Grassmannian, and let it be generated by these two vectors U and V. So we are writing each vector as a linear combination of the basis vectors of C6, which are W1 to W6. The coefficients are from C. And when is U2 isotropic? This is if and only if these two vectors vanish identically. When we do the computation with the matrix, we get this expression. When we group the first term with the last one, we see that this is a determinant of a subminor of the corresponding matrix representing U2. So it is a subminor containing columns 6 and 1, or columns 1 and 6. And this is the Pulka coordinate. So we can do the same for the remaining terms. We can group them, the second one and second last, and also the inner two. So we get this relation. So we see that amongst the Pulka coordinates, we have we have a linear relation. This can only mean we don't need all the Pulka coordinates, but we shall see which ones we shall keep and which ones we shall not allow into our basis. So we're writing into our notation, we have this relation in red. We are just putting in our notation where we said I bar is 2n plus 1 minus I. Okay. So for now, we have not made everything explicit, but let us denote all relations which are raised this way by SL, and we call such relations symplectic linear relations. Now, what was proved by De Concini in 1979 in his paper of standard symplectic tableaux, his proofs in that paper imply that these quadratic relations and the linear relations generate the defining ideal of a complete symplectic Frege variety. And also, it is a prime ideal, since, of course, the complete symplectic Frege variety is irreducible. Now, let's give an example. For n equal to 2, the corresponding Frege variety will be generated by variations. The first one, for example, in this case, n is equal to 2, so we can only take sequences of length 1 or 2. And so if we take a relation where the first sequence is of length 2, and that is sequence 1, 2. The second one is of length 1. We choose 2 bar. So so we can exchange 2 bar by all indices of the first sequence. So I am seeing if I can annotate on this, but it seems it's not enabled. Yeah, so I wanted to annotate, but yeah, never mind. I will just explain by mouth. So so the first exchange will be, so we will exchange 1 with 2 bar. So we'll have, yeah, 2 bar 2, and then in this position we shall have 1. Then the next time will be, so we will, yeah, so we will have 2 bar 2 and 1, and then we will have 1, 2 bar and 2, because we're extending subsequences of length 1 with subsequences of length 1 from the sequence 1, 2, yeah. But from our expression, we had a minus, but as we said, we have these indices, the determinants are antisymmetric, so when we have to swap to make it in increasing order, then we change the sign to plus. Likewise, one obtains all the other relations. So we have all of them like that. And in addition, the corresponding linear relation. So this is the complete ideal or the full ideal for, yeah, for this variety in this case. Now, before we go on, we would like to give an approach from representational theory, because it will be useful for us. And if we consider the symplectic group, and we take this Lie algebra, and we take the set of all dominant integral weights. Yeah, so for every dominant integral weight, we have a simple module. And so if we take a highest weight vector inside this module, we can say what the complete symplectic regularity is from the view of representative theory. So when lambda is regular, meaning if it contains all weights, and we take the closure of the orbit of the action of this symplectic group on the highest weight line corresponding to this highest weight vector. So this is what we call the complete symplectic regularity. This is coming because this group has an action on the project vectorization of this module, which is appearing on the right-hand side here. So yeah, this closure is, this orbit closure is the complete symplectic regularity, which is actually coinciding with what we defined before. By the coincidence, maybe we're not talking about it for now. So, so to this variety, we can, yeah, so we can talk about this coordinate ring, because we know the defining ideal, this will be a quotient of the polynomial ring by this ideal, which we saw, the defining ideal I. Now, before we continue, because we have something like degeneration in our talk, let's first say what a flat degeneration is, because, okay, in principle, degenerations of varieties, like you begin with some variety, and then you want to make it simpler while keeping some invariance, keeping some properties. And but some which are interesting are flat degenerations. They preserve more properties than other kind of degenerations. So there are very many kinds of degenerations of varieties. This is a very big topic. But in this case, what is a flat degeneration of a variety X?
Yes, can I ask a question?
Yes, please.
Okay, so I'm looking at your previous definition. So let me try and understand that. So you've got this highest weight vector. Is it, how do you pronounce it? Is it that a new lambda?
Yeah, new lambda.
Okay. And then we apply the symplectic groups to that highest weight vector, and that, so we take all elements in the symplectic group and we hit them on the highest weight vector, and that generates some other vector in our vector space. And the set of all those vectors, that's that SP2N acting on new lambda.
Yeah.
Shouldn't that be the whole space? Shouldn't that be the whole of V lambda? Because V lambda is irreducible. So if that's not the whole of V, then V wouldn't be irreducible, or what?
Okay, so we are doing this in this projective space, and we're acting on the class of this highest weight, on this highest weight vector. So actually, I can't write on this, but I would like to write this. This is a multiple of C with nu lambda. But I think I get your question.
Mm.
However, it's not the whole of it. It's not the whole of V lambda.
Okay, that's interesting to me. That's surprising to me.
Yeah, maybe there is something which I'm missing, which I have not explained well, but it's not the whole of V lambda.
Okay.
Yeah. Yeah, okay. So we say a variety X naught is a flat degeneration of a variety X. For our case over C, if there exists a flat family, so this is a flat family is a flat a surjective morphism of varieties. So for our case, we want a flat family xt to C and a point in the base, which is a C. It's like that the fibers over this base for every t different from some special point chosen should be isomorphic to our original variety, and whenever this t is different from our special point P, then we have the isomorphism to X naught, which is the flat degeneration. And in such a case, we call X the generic fiber, while X naught is called the special fiber. So having talked about degenerations, now let's narrow down to our particular case of degenerations, which are PBW degenerations. And this PBW comes from the name Poincaré-Markov bit, which is coming from their theorem, which gives a basis for the universal enveloping algebra of Lie algebras. So for our case, let us fix the symplectic Lie algebra, because we are working in the symplectic case. And let's take a Cartan decomposition into upper triangular elements, N plus, and diagonal elements, H, and then lower triangular elements, N minus. And let's take the universal enveloping algebra of N minus. So it is known that V lambda, so V lambda is UN minus acting on the highest weight vector nu lambda. And actually there exists a degree filtration on this universal enveloping algebra, namely by fixing a degree, fixing a natural number S, and then taking products of elements such that when you add their degrees, when you add the number of n should be less or equal to S. So we are putting everything in compartments. That's why we are calling it a filtration. And such a filtration induces a filtration on the whole space V lambda, because we have that V lambda is UN minus acting on nu lambda. So we have this filtration UN minus S acting on V lambda on the whole space. And such a filtration is called the PBW filtration. Now, let us call V lambda A the graded space associated with the filtration Fs. Yeah, and have I said what Fs is? Okay, yeah, Fs is UN minus S in lambda. So yeah, so V lambda A is this graded space, which is F naught direct sum with this quotient. So F naught is the highest weight line. We want to keep it. And then we take the quotient of, so we have all elements of degree S, and then we filter out all elements of lower degree. And now this space is a module over some Lie algebra, which is the direct sum of the Borel subalgebra of the original Lie algebra, and some abelian ideal, which is n minus a. We are denoting it by n minus a. The a is representing abelian because we are making n minus abelian we're making everything to commute because of such a filtration. Now, if we take the corresponding Lie group, denote it by sp2na, and we take the so we take the image of our highest weight vector like we had before in this new graded space. Now one can again define what the PBW degenerate flag variety in the symplectic case is, and we want the complete one. So when lambda is regular, we get such a variety, and we denote it by the same symbol, but we attach an A. We append an A to show abelian, and this is again the action of this group on this highest weight line, and we take the closure. So we have from the side of rep theory, this is the complete symplectic PBW degenerate flag variety. But as it is now, it is difficult to do geometry on it. So again, we shall run back to linear algebra to make it more explicit and easier to work with. But as we know, the building blocks for flag varieties are Grassmannians. So in our case, we need to understand what symplectic PBW degenerate Grassmann varieties. So coming back to linear algebra, we can, let's say C2n, let's call it W to simplify notation, and let's take this decomposition, the decomposition, having components WK1, WK2, and WK3, where the first one is the span of all basis elements of W. So we've taken the first K vectors, we take the span of this. And then the second component, we take the next from K plus 1 to 3n minus K. And the last one, we begin from 3n minus K plus 1 to 2n. Now let's consider this projection. So we project along with the second factor, along with the second component, meaning everything in the second component will be sent to 0 while keeping the others. So we have that. And now what was proved by Feigen, Finkelberger, and Littleman in 2013, they proved that the symplectic PBW degenerate Grassmann variety, which we just denote by the same symbol, but we attach an A to show degeneration, is given by the set of all subspaces from the usual Grassmannian, but we require that the projection of these subspaces under the above projection PR13 is isotropic. So we no longer require the whole, the subspace to be isotropic, but we require their projections to be isotropic. So they proved this elegant result, and now having known what symplectic PBW degenerate Grassmann varieties are, we can now talk about the complete symplectic PBW degenerate flag variety. And for this, we need to introduce more projections. These are different from the ones from the last slide. So for these ones, we project along one coordinate. So we are just killing one coordinate and keeping the rest. And what they proved again, in the same paper by the same authors, they proved again that this degenerate variety is naturally embedded in the product of degenerate symplectic Grassmannians. And they proved further the image of this embedding is given by the collection of all subspaces, such that when you project along K plus 1, the coordinate K plus 1 of UK, this one should lie in UK plus 1. So K from 1 to n minus. And the extra condition, like we would expect, that you will need now every subspace to lie in the symplectic degenerate or PBW degenerate Grassmannian variety. This is the extra condition, or what we can call the isotropic condition. Now they proved further that this variety, recall we gave the definition of a flat degeneration of a variety. So they proved that this variety, the complete symplectic PBW flag variety. It is a flat degeneration of the classical counterpart, and it is also an irreducible variety. Now, so we know this, we know we have an embedding of a variety into some, again, projective space. We can again talk about a polynomial ring, having all these variables like before, but now we put an A to mean degenerate. And now I want to look at degenerate relations, which can define our variety again. So, but we need a tool, because at the moment we have the classical relations. We want to understand how we can arrive at new relations we can define, which can define our degenerate variety. So this tool is a degree, which is coming from the PBW filtration. And this degree is called, because of the name, PBW degree. So it can be defined for the sequence J, but also, which can also be transmitted to the coordinate xj. So this will be all indices in that sequence, which are bigger than the length of the sequence. So in this case, the length of the sequence is k. Now, what Fagin proved in his paper about degenerate PBW flag varieties, it was done for type A. He proved that these relations are actually, okay, he obtains relations from the original Plicka relations by using this degree, which I will explain how this is done. So what he does, he picks out terms of minimal PBW degree from the original Plicka relations. So, and then he maps every variable. He attaches an A on each variable. So yeah, if you have a product, then you give a degree to each of the variables. Then for the product, you take the sum. So we have the same relations, but now we have only terms which are having the minimum PBW degree. Now, again, of course, one can ask that, are these relations enough? Of course, there is no chance, because they were not enough in the first case, in the classical case. So they can't be enough again in this case. So we need extra relations again. So again, we can do some small example for n equal to 2 for the symplectic PBW Grossman variety of two-dimensional subspaces. Yeah? We need these ones to be, we need the projection of this subspace to be isotropic, the first projection we gave. So like we saw before, we had some vectors generating this subspace U2. We can take the same vectors U and V, but now we are going to project using the previous projection we had PR13, which projects on the second component. So in our case, the first component will contain vectors W1 to W2, and the last component will contain vectors from W5 to W6. So the middle component with W3 and 4 will not appear here because those are exactly the vectors or the elements which are sent to 0. So we do this for the two basis elements, and now we want U2 to be isotropic under this projection. So this is the case when this is true. So when we do the computation, we have this relation. So in this case, we see that there are some two terms which have disappeared. And so we have a degenerate symplectic linear relation. If we associate in the same way Plicka coordinates, the first term and the last one will give a determinant corresponding to this, which is the Plicka coordinate x16. So we attach an A to just mean degenerate. And likewise the inner two. So there is a term which has disappeared. And if you write in our notation, we have this expression in brackets. Now, it is apparent one gets the same relation by picking out terms of minimal PBW degree from the original relation we had. Yeah, so if we give degrees to these terms, the first one has degree 1 because the number of indices is greater than the length of the sequence, which is 2 in this case. Here it is 1, so the degree will be 1. Here the degree will be also 1, but here it will be 2. So when we pick out terms of minimum degree, we shall keep x1 1 bar and x2 2 bar. That's why we have this relation. So on one side, one is beginning from linear algebra and getting relation. And then on the other side, one is using a degree coming from rep theory, representative theory, and arriving at the same relation. Now, since we have not made everything explicit, let us just again denote all such relations by SLA. Now, the main result in what we have done so far is that this ideal IA generated by these degenerate relations, the quadratic ones and the linear ones, is the defining ideal of our complete symplectic PBW degenerate flag variety. And it is also a prime ideal. So, so we can illustrate how to obtain these relations. So like we said, we begin from the original relations and we pick out terms of minimum PBW degree. As you can see here, there is a term which has disappeared and it was x1 2 bar x2. Now, if we compute the degrees, this is the term is degree 2, and this other two have degree 1. Because this one has the first coordinate here, x1 2 has degree 1, and x2 bar has degree 1 also. No, the first coordinate has degree 0 because there is no element which is bigger than the length of the sequence. So the degree of this one will be 0, while the degree of this one will be 1. Likewise, the degree of the variable x2 2 bar will be 1, while the degree of x1 will be 0. So the degrees of the two are just 1. And then the other one has degree 2, so that's why it is not appearing. We do the same for all the other relations. And also the symplectic one, the linear one, the two terms have the same degree, so they will remain. Now, for the rest of the talk will be dedicated to proving our main result. So for this, let us introduce the homogeneous coordinate ring of this variety. We will denote it by CSPF2NA. And if we say that JA is the defining ideal, the actual one, because IA, we don't know yet if it's the defining ideal. So let's call JA the actual defining ideal. Then if we know this, then one can say that if we take the quotient by this ideal from this polynomial ring, which we saw before, then this is the coordinate ring. And this coordinate ring has a decomposition in terms of these dominant integral weights. And so these are the homogeneous components. And this is isomorphic to a direct sum of some dual modules, because we know that every symplectic flag variety is corresponding to some dual, to some module. In this case, the module V lambda A, the degeneration of the original modules. So if we take the dual and we take the direct sum, we have an algebra structure on such a direct sum because of an existence of a unique injective homomorphism of modules, whereby we embed for any two dominant integral weights, we take the sum and we take the corresponding module and we embed this in tensor product of the individual modules. And the injection is by sending the highest weight vector in the first space to the component because on the right-hand side, we have a bigger space. So we just send to this component, the corresponding component. So when we take the duos on each side, like we take the duo of v lambda plus mu a, and we take the duo of v lambda a mu, then we shall have a surjection going backwards. So this surjection gives the multiplication on this direct sum, hence making it into an algebra. And this was proved by Fagin, Fourier, and Littleman in 2011. So the isomorphism which appears here, so we can just compare components. For example, we can compare components. So this component CSPF2NA lambda is isomorphic to the corresponding dual space. And this follows from an analog of the Borel-Weil theorem. This analog was proved by Fagin, Finkelberg, and Littleman in the paper we saw before, where they look at symplectic degenerate flag varieties. So, so at this point, we are going to now move on and establish a combinatorial flavor, which will help us to obtain our main result. Now, so these objects are called symplectic PBW, semi-standard tableaux. So, but we want to associate this to flag varieties. So, and the flag varieties are defined with respect to some weights. When you look at the representative theory site, so it is natural to associate a partition to a dominant weight in this way by adding all multiplicities from 1 to n. Then to give the first entry, the next one will be m2 plus mn and so on up to mn. This gives a partition. And to such a partition, we can associate a Younger diagram, which I will take the English conversion. And yeah, so one can ask what is the set of tableaux that labels the basis for both the coordinate rings for the classical case and the degenerate case. So one can start from Younger tableaux. These are the most common elements in representative theory of groups and Lie algebras. So let's recall briefly what they are. So if we have a partition, a general partition lambda 1 up to lambda n, so we can associate a Younger diagram like before we said, and if we take entries from this set which we had before, 1 to n bar to 1 bar, which is actually the set 1 to 2n, yeah? And so we want that in our Younger diagram, we fill entries such that downwards they're strictly increasing, and across they're weakly increasing. Weakly increasing meaning they can be equal. Two consecutive entries can be equal. This is the condition written here. So now let's define what a PBW tableau is. Okay, I should say that there are very many tableaux in the symplectic case. For example, tableaux of King, ones of De Concini, tableaux of Kashiwara Nakashima or Proctor. Yeah, very many. Yeah, but all of them build on semi-standardness coming from Younger tableaux. So they satisfy these conditions we have seen, this definition plus extra conditions. So the reason why PBW tableaux were introduced by Fagin was because he wanted to label a basis for both of these two coordinate rings in type A, but Younger tableaux failed to do so because something happens which maybe time will not permit to talk about now. So Younger tableaux are not suitable to label a basis for, especially for the PBW degenerate, the coordinate ring of the PBW degenerate flag variety. So that's why he defined a new tableaux Yeah. So let's see what these tableaus are. So right now we have a different feeling of these Young diagrams. So we want that entries which are less or equal to the length of the column, we want them to be at positions which have position number equal to these entries. And we say that such entries are at their positions. For example, 1 is at position 1, so we say it is at its position. So whenever we have an entry less than length of the column, it should be at its position. Likewise, you see 3 is at its position, but 1 bar is not less than the length of the column. So it should be filled in such a way that it is bigger than the entries below. So entries which are not at their positions should be filled such that they are bigger than entries below. So these are the two conditions here. And we say that such a tableau is PBW-semistandard if in addition, beginning from the second column, if for every entry in the second column, so for example, we take an entry 2 bar, we look at the column to the left, and we want that there is an entry in the same column or below, which is bigger or equal to this entry. So this is the condition here. And now what we found out after in our work, I found that beginning from such tableaux, one can arrive at a set of tableaux for the symplectic case by imposing an extra condition. So this condition says, whenever you have an entry which is less than the length of the column, which is at its position, and we have also, for example, we have an entry I, and we have also I bar in the same column, then I bar should be above I. So this is the extra condition which should be satisfied for us to obtain a set of symplectic PBW tableaux. Now for n equal to 2, the full set is here. There are 16 of them. So these are the symplectic PBW tableaux. As you can see, every element here should have an entry here or below, which is greater or equal to that. And so let's come back to, I think I have to hurry up to, what time is moving. So, so let's come back to the symplectic linear relations again. Now for, for a sequence, we can arrange this sequence in terms of, into a tableau, a PBW tableau. And if this doesn't produce a symplectic tableau, we call this sequence non-symplectic. So the linear relations we saw before actually can be interpreted in terms of these tableau columns. In our work, we proved that there's a correspondence between such columns and such sequences and tableaux. So because of time, I avoided including a lot of notation, but I'm just using this, which we can use now. So these sequences are giving us a way, these relations are giving us a way of writing a variable which is corresponding to a non-symplectic sequence as a sum of symplectic ones. So we can replace a non-symplectic variable as a sum of symplectic ones. So we can do this, for example, if we recall this relation which we had before, this one arises this way. One can see that 1 bar is not symplectic because it violates the symplectic condition, but the other two are symplectic. So this relation will give us a way of replacing this x1 bar by a sum of these two. And these relations were defined by De Concini in this paper, which we saw before in 79, but in a different way and different notation, which I have avoided talking about in this talk. Now, so what is apparent about these relations is that they are compatible with PBW degree in such a way that if you look at the PBW degree of this term corresponding to a non-symplectic sequence, it will, this PBW degree will be the lowest, will be among the lowest. So, and the others will have a degree greater or equal to this one. So this one means that if we take the degeneration of such relations, then the term corresponding to non-symplectic sequence will remain in our relation. So this one will be useful later on. And now, so another important property of these tableaux is that they are in a weight preserving bijection with some nice mononomial basis for these modules we saw before. How nice it is, maybe if someone asks later. And maybe let's talk about the proof of the main result briefly. So to every tableau, we can associate a monomial by taking, so in a tableau, for every column, we can associate a variable indexed by these elements in the column. And we take the product of all of these variables corresponding to all the columns. So this will be a monomial. And we do this also for the dual module V lambda A. So these elements are living, the first one in V lambda star, which is the dual module corresponding to V lambda, and second one in the corresponding dual module. So what we proved also is that the set of tableaus of symplectic PBW tableaux labels the basis for these homogeneous components, these respective coordinate rings in the degenerate and classical case. The idea of the proof, first of all, from the previous result we saw, we know the number of tableaux is equal to the dimension of these modules. And this means that we have the right number of elements. So what we need to show is that these elements are spanning our coordinate rings. And we are, for our purpose, we shall just look at the degenerate case. Now, how do we do that? So briefly, we start with an element XTA, which you saw from the previous slide, for T symplectic but not semi-standard. And we want to write this as a linear combination of symplectic ones. So because semi-standardness is defined between any two columns, two neighboring columns, it's enough to reduce the proof to any two columns, to any two neighboring arbitrary columns, L and J. So if we take two such columns which violate the condition of semi-standardness, what Fagin proved is that the term corresponding to such columns will remain after degeneration. He proved this in his paper. And he also proved that applying these relations which we saw will lead to smaller tableaux with respect to some fixed total order. Now, what remains is to make sure that every tableau appearing will be symplectic. So, but because these relations are exchange relations, so when you exchange, it is possible that some column will become non-symplectic because you're moving around indices. But you want to make sure that in the end, after the process of exchanging and so on, everything will become symplectic and semi-standard. So we can use our relations, the linear ones, the degenerate version of the linear relations we saw before. Lucky enough, we know that the term corresponding to a non-symplectic column always will remain. So we can always apply these relations. And what we proved is that, when we apply this relation, the terms become smaller with respect to the same fixed order. And so we have two finite processes. We are replacing two things at the same time, and such a process should terminate. And therefore, it should be possible to write a non-symplectic, non-semi-standard tableau as a linear combination of symplectic, semi-standard tableaus. So we can see that these terms span this coordinate ring. And now the idea of the proof of many result is that we have used our relation to rewrite everything as a basis for this coordinate ring. So this means these relations provide a straightening law for rewriting something which is not semi-standard, not symplectic, as symplectic semi-standard. So there is a result which says whenever you have relations which provide a straightening law, then such relations should generate the defining ideal with the corresponding variety. Now, this variety is prime because this Degenerate flag variety is irreducible. We saw this in the result of Finkelberg and Littleman. They proved that this variety is irreducible. Actually, they proved it even more. Now, so coming to the end, finally, in a work in progress, we are extending this construction of type D to flag varieties of type D, the even orthogonal flag varieties. So we are trying to define tableaus in the same way, and also to study coordinate rings and relations which are defining them. And also we are studying at the same time in the tropical symplectic Grassmann and flag varieties and corresponding toric generations. Because when someone has the ideal defining a variety, it is natural to look at such objects. For example, the tropical variety and toric degeneration of such varieties. So that's the next step we are taking. And on the other hand, one could investigate if the odd orthogonal PBW degenerate flag variety, namely, if we take the Lie algebra of type B, is a flat degeneration of its classical counterpart. Up to now, it's not yet done, but there is some kind of, on the side of rep theory, something has been done, but on the side of flag varieties, nobody has done this yet. So one could look at this also. It could be interesting because, as I said, people study these varieties in case by case.